Okay, we learn how to find the limit by looking at the graph or make a little table. The table has two rows, right? We have x approach to a number from left side and the right side, and then we find what the function value would approach to. So we can find the limit. But sometimes you're not very lucky. For example, I give you this example. I ask you to find limit when x approaches to 0, x over absolute value of x. Find this. And of course, you don't want the denominator to be 0, so the definition or the domain should be all real number except 0. That's what we know. Okay, as a quick review, the concept of absolute value. Absolute value of x is that x itself when x is greater than or equal to 0 is negative x when x is less than 0, right? When x is negative, then after you take the absolute value, you get the opposite of it. So like negative 5, the absolute value will be positive 5. But the absolute value of a positive 5 is 5. Absolute value of 0 will be 0. Now in order to find this, let's make this little table. We have x, and we have x over absolute value of x. Now, we want x approach to 0, okay? I don't do anything about that. I just go from left to 0, from right to 0. So I go from this 0 0.1, 0 0.01, 0 0.001. I just want to see the trend. So negative 0.1, negative 0.01, and a negative 0.001. I think I can stop there. When x equals 0.1, it's a positive number. When x is a positive number, then the absolute value of x is just the x, and x over x is 1. So that's 1, here's 1, here's 1, and we don't care about this. When x is a negative number, then the absolute value of x will be negative x over negative x. So I got a negative 1 everywhere on the left side. Okay? And when here there's no definition, when x equals 0, there's no definition because that's not in the domain. If you graph that, you're going to get something look like this. Here's a x, here's a y, and a 0, okay, 1, 1. You're going to have, when x is greater than 0, you get a positive x, then the function value is always 1 with a circle. Okay, so that's the graph of it. And when x is negative, that means from 0 to the left, then the function value is negative 1. So you have this line. And again, there's a circle. The circle means there's not defined at this point. All right, now the problem is when x approach to 0, the function value will approach to different number. Okay, so this is one of the case. We call that a different right and left behavior. They're different. So we say this limit does not exist. Okay, does not exist. So this is a very interesting situation, right? So we found one example that limit doesn't exist. Let me give you another example. I ask you to find limit when x approaches to 1 over x minus 1 square. Okay? Again, x cannot be 1, right? Because when x equals 1, then the denominator becomes a 0, it's undefined. So we're going to have x, come up with those table, and 1 over x minus 1 squared. If you cannot do this quickly, then you can use another way. You can use this. You can do this. You can do what is x? What is x minus 1? And what is x minus 1 squared? You do this step by step, and then 1 over it, x minus 1 squared. You can do that. So it just gives you like a multiple rows. But this is x, and this is y. So in the future, you don't really need those values. It just help you to get the answer. But let me do that. So when x approaches to 1, which is invisible 1, I'm going to write it. So I get a 1.1, 1.01, 1.001. And here I get a 0.9, 0.99, and 0.999. Okay, when x equals 1.1, when x equals 1.1, minus 1, I get a 0.1. You square that, get a 0.01. And a 1 over means you flip, take the reciprocal, you get a 100. Okay, so here's 100. Now you see why sometimes you might want to use this method, because you go further, a little bit more steps. If it's x is 1.01, then you subtract a 1 first, you get a 0.01, square it, you get a 0.0001, 1.01, subtract 1, you get a 0.01, square that, you get a 0.0001, and then you take the reciprocal, you get a 10000, so that's 10,000. So here is a 10,000. And for this 0.001, you follow this, okay? I didn't leave enough space, but if you want to do that, you can do this. You can do that step by step. 1.001 here become 0.001, 0.000001, and then square that, you get a million. So you get a million. Okay. This gets greater and greater. And this side, when x equals 0.9, you minus 1, 0.9 minus 1, you get a negative 0.1. And then you square that, you get a positive, right? Square of a negative number is a positive. So 0.001. And then you take the reciprocal, you get a 100. And I just write it because I already know the answer. Okay. All right, now, did you notice that when x approaches to 1 from left side or the right side, what happened to the function value? The function value approached to infinity, isn't it? Okay, so there's no single number. It doesn't approach to a single number. So when you graph that, it goes like this. It goes like a 0, that's x, and that's y. Guess what? You have something look like this. So that's the graph of your function. Did you see that when x approached to 0 from the left side and the right side, your y or your function value approached to not a fixed number, it goes to infinity. So in this case, this limit does not exist. Okay. Or another way, you can write it like this, if you want. X is greater, approaches to 1, 1 over x minus 1 square, that's positive infinity. All right, so far so good? All right, now we are going to work on the last example to show you that sometimes the limit doesn't exist. The question is this. Find the limit when x approaches to 0, sine 2 over x. It's a very complicated function. Okay, so this limit as x approaches to 0, sine 2 over x, what's the limit? When x approaches to 0, let's see. I made some numbers up because I already know what's going on, but I want to show you this. So let's do that because it's not that obvious. So let me just write x value and then 2 over x and then sine 2 over x. Is that okay? Or you want one more step? You want to get an x, then do this. You get an x, then x over 2. Okay. So if I give it some x value, then you have, because you want to see this, So x over 2, and then you flip it, and then you take sine of it, okay? So let me give you this. You might wonder later, how do you know? Well, it's a 4 over pi, 4 over 3 pi, 4 over 5 pi, 4 over 7 pi, 4 over 9 pi. Did you notice that 4 over pi is greater than this 4 over 3 pi? It's greater than that because the higher the denominator, if they have the same numerator value, then this fraction gets smaller and smaller and smaller, and it goes to like a 4 over, I don't know, 101 pi, okay, 4 over 103 pi. You can continue, okay? Now, if this is an x, then what is x over 2, which is just half of that? So it's going to be 2 over pi, 2 over 3 pi, 2 over 5 pi, and a 2 over 7 pi, and a 2 over 9 pi. I'm lazy, I just don't want to do that. And then the next one is, the next row, we're going to do 2 over x, which is flip or reciprocal of that. So it's going to be pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, etc. Next, sine 2 over x. So this is the angle, we're going to take sine of it. Sine pi over 2, which is 1. Sine 3 pi over 2, which is like a 270 degree, right? So it's negative 1. And then 5 pi over 2, 1. Negative 1. 1. Da, da, da. So did you notice that when x approaches to 0, and this sine function, it has a boundary, right? Just positive 1, negative 1, just because it's a sine function. But it doesn't approach to a fixed number. Not only that, when you graph that, you have something look like this. Here's a 1, here's a negative 1, here's a 1, here's the x. Okay. So it goes like, and this side too. So it's like a bumping around, okay? So in this case, we call this is oscillating behavior. Just shh. Okay. This oscillating behavior, it happens when you take something about trigonometric function, and because for the trig function like a sine and a cosine, you have they're periodical, right? The period is usually like it's 2 pi, but when you flip it, when you have the x in the denominator, sometimes you get this situation. Sorry, my drawing is not very accurate, but you're gonna see that. But there's no definition, so but it just gets very very close to, I don't know, to the y-axis, but never stops. So that in this case, the limit does not exist. All right, so we learned 3 different situations, the common types of behavior associated with a non-existence of a limit. Number 1, the left and the right limit are not equal. Number 2, that the function value when x approaches to the number, it goes to infinity, or it's unbounded behavior. It goes beyond some number, which no fixed number. And the third situation is oscillated between 2 fixed values when x approaches to c, or a number. In this case, our x approaches to 0. So those are the 3 common situations that your limit does not exist. See, you're not lucky all the time, right?